All right, hi you guys. So I know we're currently working in topic 5, um, but we are backtracking a little bit to do section 1.7 in Envision, which we originally skipped, because these equations are absolute value equations, which relates to what topic 5 will be about, which is absolute value functions. So we're going to quickly backtrack and learn how to solve absolute value equations and inequalities in this section. Remember that absolute value is defined as the distance from 0 on a number line. And linear equations, when you solve them, they typically have one solution. They could have no solutions or infinite solutions, but typically when we solve a linear equation, it has one solution, x equals a number. But because there are two values that are x units from 0 on a number line, an absolute value equation will have two solutions. So what I mean by that is if you had a number line and 0 was here, and this is positive 2, and this is negative 2, there are two values that are 2 units away from 0 on a number line, positive 2 and negative 2. So absolute value equations are going to have two solutions. Because absolute value implies two solutions, solving absolute value inequalities will be kind of like solving compound inequalities, where we had and inequalities and or inequalities that showed one section of a number line or two sections pointing in opposite directions. Okay, so let's look at some different types of examples here. Some examples will have just x inside the absolute value bars, or just the variable inside the absolute value bars. If that's the case, we're going to isolate the absolute value expression on one side of the equation. So we want to isolate the absolute value of x. Right now in this equation, that means getting rid of plus 2 by subtracting 2 on either side, which leaves me with 5 equals the absolute value of x. So we isolated the absolute value expression. And now that I have that, I know that there are two numbers that when I take the absolute value of those numbers, it equals 5. And that's positive 5 and negative 5. Because the absolute value of positive 5 is 5. Because 5 is 5 units away from 0 on a number line. And the absolute value of negative 5 is 5. Because negative 5 is 5 units away from on a number line as well. So my two solutions are x equals 5 and negative 5. Now let's look at an example where it's not just x inside the absolute value bars, but it's an entire expression. Once again, you'd want to isolate that expression, but it's already isolated, right? There's nothing else on this side besides what's inside the absolute value bars. So our next step is to solve for the two possibilities, which would be negative and positive. So I'm going to set this absolute value expression, 2x minus 3, equal to positive 1, which is exactly what it looks like here. And then I'm also going to set the absolute value of 2x minus 3 equal to -1. Okay, because these are the two possibilities for absolute value. And now I can solve them like normal. So I can ignore the absolute value bars and just solve 2x minus 3 equals 1. So I would add 3 and have 2x equals 4. And then I'd divide by 2 and see that x equals 2. And then over here, I would add 3. And this would be 2x equals 2. And I would divide by 2 and have x equaling 1. So here I have two solutions as well, just like I had two solutions up here. But this time my two solutions are x equals 2 and x equals 1. And I'll prove that to you really quick and just show you why. If I plug 2 in to this equation, 2 times 2 is 4, and 4 minus 3 is 1, and the absolute value of 1 does equal 1. When I plug in 1, I get 2 times 1, which equals 2, minus 3, which is -1. But the absolute value of -1 is also 1. So that's why we set it to the positive and negative versions of the answer. Okay. Finally, we have a problem where the absolute value expression is not just the absolute value of x, and it's not isolated. When this happens, you need to isolate the absolute value expression first. Okay, so I need to get the absolute value of x plus 6 by itself before I do anything else. So to do that, I'm going to almost treat this like it's in parentheses, and that's what I want by itself. So I'm going to get rid of the constant, which is positive 8, by subtracting 8 from either side. And this equals -3. And then I have 3 times the absolute value of x plus 6 equals 3. And then this is multiplication, right? So 3 times the absolute value of x plus 6. So I can get rid of that 3 by treating it like a coefficient and dividing by 3. And I have to do that on the other side too. So then I have the absolute value of x plus 6 equals -1. Now this is isolated, so now I can think about solving it. However, I'm going to read this line up here. If the absolute value expression is set equal to a negative number, there is no solution, because the absolute value of a number is a distance, and it can't be negative. So this is quite tricky, because up here, when we were solving, we set our expression equal to a negative, but that was just to find the actual answer. The actual expression was not equal to a negative originally, here or here, right? It's when it's equal to a negative in the problem that it's no solution. So cannot equal a negative. So no solution is my answer. Okay. Lastly, we're going to look at inequalities. So as we set up here, we're going to kind of treat these like they're compound inequalities. When you have the absolute value of x as less than a number, that's going to be like an and compound inequality. So we have x is less than 3, and then if you think about it, it would be like negative x is less than 3, but when we divide by a negative in an inequality, we flip the symbol. So, and x is less than, or sorry, is greater than, 3. So x is less than 3, and x is greater than negative 3. I'm just going to cross this out because I messed that up quite a bit. X is less than 3, and x is, flip the sign, greater than negative 3. There we go. Remember, we can also write this when it's an and inequality as like one expression where x is in the middle. So x is less than 3 and x is greater than negative 3. Both of these mean the same thing. Okay, and then we can graph that on a number line. So these would be open circles since it's not or equal to here on negative 3 and positive 3. And we would shade in the middle or connect these dots in the middle because x is greater than negative 3 and it's less than 3. So it's somewhere in between here. Over here, when we have a greater than symbol in an absolute value inequality, that's going to present itself as an or compound inequality. Because if you think about it, we've got x is greater than 3, or if this were to be negative x is greater than 3, we would divide by negative 1, flip the symbol, and we would have x is less than negative 3. This I don't write as a compound because these are two different things, two different sections on the graph. I'll make it a little longer here. Once again, my circles are going to be open because it's not or equal to signs. So open on positive 3, open on negative 3. But this time my arrows are going to be pointing in different directions because x is greater than 3. Or x is less than negative 3.